get started. So this is the final session of the conference on algebraic and circuit complexity. And the first talk is on complexity measures on the symmetric group and beyond. And Nathan is going to give the talk. So Nathan.
Great. Okay, so so let's just get right into it. Okay, so recall that the definition of Fourier degree on the hypercube is as follows. So here f hat of S, this denotes the Fourier coefficient corresponding to the subset S. And also recall that this coincides with the definition of the degree of f as a real multilinear polynomial. Okay, so that was Fourier complexity. Let's talk about decision tree complexity. So decision tree complexity is defined as follows. It's the least possible depth of a decision tree T that computes a Boolean function f. So the following two facts are known about the relationship between the Fourier complexity and decision tree complexity. And when you have two theorems of this nature, we say that these two complexity measures are polynomially related. Okay, so we won't have time to even scratch the surface of all these different complexity measures that are out there. But just bear in mind that all the natural ones that folks study tend to be polynomially related. Okay, so this talk's all about going beyond the hypercube. And there's a lot of recent work in theoretical CS that has done so. Here's just a few works that I know of from the past 2 years. It's by no means comprehensive. But a perfectly reasonable question at this point is to ask whether or not we can export our Boolean functions toolkit to these other more exotic combinatorial domains. And one wouldn't want to do this on an ad hoc basis. So really the question is there a good abstract framework for studying complexity measures on other combinatorial domains? And here I've just listed a few combinatorial domains, again, not comprehensive, but is there an abstract domain that captures all of these maybe? Sorry, an abstract framework that captures all these. So one of the merits of our work is that we propose an abstract simplicial complex-based framework that captures many, but not all of these combinatorial structures. Okay, just to give you a taste of what this framework looks like, we start off with the universe of atomic symbols, and then we define a domain, and the domain is just a set X whose members are n subsets of U, where n is some fixed natural number. Okay, so we want to do things like define decision tree complexity in this abstract framework, so we need an abstract notion of what a query is. And that's defined as follows. It's just a subset of the universe that intersects each member of my domain in exactly one point. And with each domain X, we associate a set fancy Q of allowed queries. Okay, and so there's a lot of other parameters that are needed to formally define these other complexity measures to these in this more general setting. Please consult the full version of the paper on the archive for these details. So let's just take the hypercube. How do we squeeze the hypercube into this abstract framework that we've defined? Well, first we let our universe be the following Cartesian product. And now we're going to identify each bit string as follows. Okay, so it's a very natural identification here. And let's consider a different domain. How about permutations? So what should the universe be for permutations? Well, it's this Cartesian product. And we make a similar identification here. So I comma pi I, where pi I is the image of I. Right, and so you can do this for a variety of other combinatorial domains. Again, see the full version of the archive paper if you want to know how we were able to model some of your favorite combinatorial object as in this simplicial complex framework. Okay, so let's revisit decision tree complexity. So recall that with the decision tree complexity of the internal nodes, these represent queries, and so we're asking whether or not index I is a 0 or a 1. So if we now look at permutations, there's a very natural analog of this. And so instead of asking if each coordinate is a 0 or 1, we're asking questions of the following sense. So of the following type. So like for permutation pi, where does I get sent? Or what gets sent to K. These are the queries that we're asking in our internal nodes. And notice that I've omitted some nodes here to keep the picture brief, but each internal node has n children. And so now we just have the same definition as before for decision tree complexity for permutations. So the decision tree complexity of a function is just the smallest tree of this form that computes my Boolean function over permutations. Okay, so that just gives you a taste of just for decision tree complexity, but we were able to do this for a lot of different complexity measures. And so our main theorem is that we were able to show that all these complexity measures, when we generalize them in this abstract simplicial complex framework, they're all polynomially related. And we're able to do this for a bunch of various combinatorial domains that I won't list. Okay, so one thing that I want to point out, though, that this theorem is nice, but another main result is actually just coming up with the right definitions for these things, because it's very easy to come up with definitions for things that seem natural at first, but when you compare them to others, they're just not polynomially related. And so in the remaining time that we have, I just kind of want to walk us through this process and show you the subtleties for something as simple as, like, say, degree on arbitrary domains. So if you want to talk about degree, you need to know what a function is, or sorry, a polynomial. So a polynomial is we have the following natural definition. So it's just a linear combination of carefully chosen indicator functions. Okay, and so the degree of a polynomial is just going to be the largest S, such that its corresponding coefficient is non-zero. And now the degree of a Boolean function over an arbitrary domain X is just the least degree of a polynomial P that represents that function. Okay, so for this definition to be natural, it needs to correspond to Fourier degree, like we witnessed for the hypercube on slide 1 of this talk. So, okay, so what does Fourier degree even mean for an arbitrary X? So it turns out that the right algebraic object to consider here is the permutation representation of a symmetric group acting on your domain. And so now this admits a decomposition into irreducible representations of the symmetric group, and these are indexed by integer partitions. Okay, so now we're in a position to define Fourier degree, and that's just defined as follows. If the representation theoretic stuff is tripping you up, this is just like the Fourier degree for the hypercube, only now we're considering integer partitions rather than subsets. And our notion of size is the number of cells under the first row of the integer partition. So we draw that picture, think of it as a Ferris diagram, and look at the number of cells under the first row. Okay, so I've given two different definitions of degree here, one in polynomial land and this other one in representation theory land. And so it's not at all obvious why these things should be equal, but for many domains, it turns out that they actually are equal. And this draws upon some deep results that have been happening in extremal combinatorics over the past decade or so. So just to wrap things up, here's the degree, here's like our visualization of Fourier complexity on the hypercube. So this is what the picture looks like for arbitrary domains. So we're just swapping out subsets for integer partitions. And the notion of a size is just the number of cells under the first row. Okay, so that's the end. So let's just conclude with a few open questions real quickly. So this framework that we have doesn't capture Q analogs. So how do you do them? We don't know. Also, we've had difficulty extending our sensitivity results to hypergraphical type matchings. So see the full paper for what's going on there. Real loose vague question, but is there some sort of deeper explanation for why polynomial degree and like Fourier degree are coinciding for some of these more abstract and exotic combinatorial domains? That would be really interesting to figure out. And finally, applications. So we have this framework that we've developed, and it would be great if we could find some applications of this framework to various problems in theoretical CS. Okay, thank you very much.
Thank you. Okay, the talk went a little over 1 minute over time, so let's move on to the next talk quickly.
Oh, sorry.
The next talk, no, sorry, I didn't interrupt you. The next talk is by Jiabao Lin, who's going to talk about the complexity of counting CSP. So if you can share your slides.
So can you see my screen?
Yes, we can.
Okay, let's start. Screen mode. Okay, hi everyone. I'm Jiabao Lin. I will introduce my result on the complexity of counting CSP-D. Yes, CSP is the constraint satisfaction problem, and here the D means that every variable appears a multiple of D times. I will introduce the motivation later, but now let's start with the definition of continuous SP. In constraint satisfaction problems, we use relations to express constraints. But in counting problems, especially weighted counting problems, it's more convenient to consider functions. And when we talk about functions, we will always fix a finite domain D. In particular, if Q equals 2, and then D is called a Boolean domain. And the function of array K on D is a map from D to the K to complex numbers. Now we come to the definition of continuous SP. Let F be a finite set of functions. We denote the following problem by just SPF. An instance has some variables and some constraints. And each constraint is a function from the big F applied on the top of variables. And we say the instance I defines the function fi. It's the product of all these constraint functions. And the output of the problem is the sum of all function values of fi. And the sum is also called a partition function in statistical physics. We can use different constraint functions to express many important counting problems and the graph parameters. So the question is, what's the complexity of evaluating the partition function? Intuitively, to compute such an exponential sum, we can avoid brute force enumeration only when the function fi has a very nice structure. The idea was formulated by Jingyi Cai and Xie Chen. They prove a dichotomy theorem for continuous SP. That is, the problem such SPF is in polynomial time if the set WF satisfies 3 conditions. Otherwise, the problem is should be hard. Here, I will not introduce the 3 conditions because they are a little complicated. And the set WF contains all the functions defined by the CSP instances. And using the same idea, I can prove dichotomy theorem for continuous CSPD. The family was first considered by Huang and Lu. Here, D is a positive integer, and the problem CSPD is the restriction of CSP to the instances where every variable occurs a multiple of D times. And the criteria for continuous CSPD is similar to Neta for continuous CSP. Yes, still the 3 conditions, but now the 3 conditions are imposed on the functions defined by instances of continuous CSPD. So a question is why we need to consider continuous CSPD. In the definition looks a little artificial. In fact, they naturally arise in the study of Holland problems. The Holland is a more general framework than continuous SP. Yes, it can also express many other problems like matchings. Holland problems have been intensively studied for many years, but the dichotomy still remains open even on the Boolean domain. An interesting fact is to classify Holland problems, we will always need to build reductions from continuous SPD and other problems like matchings. So to understand Holland problems, it's very important to understand continuous SPD. Before my result, there are only partial results on the Boolean domain. And the criteria for this dichotomy is explicit on the function set f, but they are complicated to prove. And now, of course, we have dichotomy theorem for general domains, but it's too general to say much about the Boolean domain. So the second result of my paper is dichotomy for SPD on the Boolean domain. It's more explicit, and I think such criteria is sufficient for the study of Holland problems on the Boolean domain, of course. So finally, conclusions and open questions. Previous result on SPD focus on the set of constraint functions. They are explicit but complicated to prove. And this result failed to classify all problems. In this paper, I consider functions generated by F. And the ideas are from the content CSP on general domains. And I can achieve full dichotomy for content CSPD. And the proof are very simple. Of course, they are based on content CSP. Here are two open questions. The first is, can we derive explicit criteria for Boolean content CSPD? I think it's possible, but I think it's not very easy. So I think it's better to do this when we really need to do. Yeah. And then the second is, can we apply the ideas directly to Holland problems? And yes, I think these ideas are variable. And indeed, I have some partial results in this direction. And that's all. Thank you.
Thank you. So we have time for one quick question before we start the next talk. Otherwise, if not, then we can just keep the questions to the end and start the next talk. Okay, if not, then the next talk is by Josh Grochow, who's going to tell us about tensor isomorphism, complexity of isomorphism problems. Josh, if you.
Yeah. All right, do you see my slides?
Yeah.
Great. All right. Yeah, thanks, Anindya, and thanks to the organizers for all their hard work in making a great conference for us here. So I'm Josh Grochow from University of Colorado Boulder, and I wanted to tell you about my joint work with Youming Qiao from University of Technology, Sydney, on tensor isomorphism. So tensor isomorphism arises from a wide variety of different places. In graph isomorphism, it's one of the key obstacles to getting further improvements. In geometric complexity theory, it shows up when you try to understand the borders of certain complexity classes. It's been proposed as hard enough to be useful for post-quantum cryptography. It shows up in de-randomizing symbolic determinant identity testing. Turns out to be basically the same problem as classifying quantum entangled states up to local operations. And it also shows up in machine learning as the signature tensor, which is actually, for those of you who know the difference, actually a genuine tensor and not just a multi-dimensional array of numbers that ML people will sometimes call a tensor. This one is actually a genuine tensor isomorphism problem. But it turns out that prior to our paper, the complexity of this problem hadn't been very well studied. So we actually looked at many, many different problems, but I just want to tell you about 3 of them briefly here. So the first is maybe the most familiar, which is polynomial equivalence, which I'll call isomorphism, because we have lots of equivalence relations floating around. So you're given 2 polynomials, say by their list of coefficients, and you ask, is there an invertible linear change of basis, linear change of variables that transforms one to the other? The second problem we consider is matrix P group isomorphism. So I give you 2 M tuples of n by n matrices over a finite field, say invertible matrices, and I look at the groups that they generate. And because it's over a finite field, these are necessarily finite groups, and I ask, are those groups isomorphic? And then finally, the D-tensor isomorphism problem, which is basically the same as equivalence of D-particle quantum states. Here I give you 2 D-dimensional arrays as input. So instead of a matrix which has rows and columns, here we now have D dimensions, so you have rows, columns, depths, and so on up to D. And I ask, are there D invertible matrices, A1 up to AD, such that when I apply A1 to the first index and so on, and AD to the Dth index, does that transform one tensor into the other? Okay, so what's known about the complexity of these problems? Well, they're all graph isomorphism hard due to a variety of people, depending on which problem you're talking about. For all of them, the best known algorithm is essentially brute force, q to the n squared, which is your brute forcing over finding the n by n invertible transformation. And in some of these cases, there are average case q to the n results, which is always a nice improvement over q to the n squared. But in the case of group isomorphism, that's actually particularly significant, as this q to the n here is polynomial time in the order of the group. So they all sort of sit in the same land in terms of complexity. And the question is, can we formally relate them? And in particular for D tensor isomorphism, when D is like 1 or 2, it's vectors and matrices, it's very easy. But when D is 3, it starts to get hard. And the question is, as D gets bigger, does it continue to get harder and harder? Do you have sort of an infinite hierarchy? Or for quantum states, as you increase the number of particles you're looking at, does this get harder and harder? So this is a partial picture of sort of the world of isomorphism problems prior to our paper. I'll just highlight a few things: graph isomorphism, some algebra isomorphism problems over here, polynomial equivalence problems over here, ring isomorphism, tensor isomorphism, matrix group isomorphism. And you see there are many previous reductions, but it's kind of a crazy world. So the precursor to our results was a previous paper with Futonian and Sergeychuk, where we showed that for 3 tensor equivalence problems, where I could give you maybe a tuple of 3 tensors, and they're actually blocked into chunks, and you want the same matrix to act in certain places and its inverse in other places, and whatever you want, those all just reduce to 3 tensor isomorphism. And so 3TI is universal for these problems in the same way that graph isomorphism is universal for isomorphism of finitely given structures. But here, instead of explicitly given, the things are given now by bases. Okay, and so our results in this paper with Youming Qiao complement these. So the first is that for any constant d at least 3, D tensor isomorphism is equivalent to 3 tensor isomorphism. So you don't get an infinite hierarchy. And the second is reductions in the opposite direction to the results above, which is that 3 tensor isomorphism reduces to all of these other problems. And so they're all equivalent, and we call them all TI complete. So the picture, which used to look like this, now looks like this. So everything in the box is TI complete. This box over here has some footnotes because some of these results have some restrictions on which fields they work over. But morally and over many fields, they are in fact still TI complete. So it really sort of simplifies the landscape here. So I just want to quickly give you a little bit of a flavor of these reductions. This is a reduction from tensor isomorphism to alternating matrix space isometry. I won't tell you what that is, but I will tell you it's a Q analog of graph isomorphism. And Youming Qiao, my co-author, has a lot of papers now taking graph parameters and giving their Q analogs for alternating matrix spaces. So there's a whole emerging theory there. And okay, you know, I haven't told you what's going on here, but you can sort of see I have some tensor A here, and I do minus A transpose here, and I have some identity blocks here. It's a gadget style reduction. It's in 3 dimensions, so you have to, you know, it's a little bit complicated to think about, but it's a gadget style reduction. But the reduction from D tensor isomorphism to 3 tensor isomorphism really looks different. And for that, we go through algebra isomorphism, and then we appeal to previous results that reduce algebra iso to 3 tensor isomorphism. And what the algebra we use is a quotient of the path algebra of this graph you see here, or this multigraph. And you could write down this whole thing as a big tensor with various 1s and 0s and coefficients all over the place, but it would be a big mess. But when you phrase it in terms of these algebras, a lot of it pops out nicely. And we really do use sort of, you know, the full meat of the theory of associative algebras. The Jacobson radical, the Wedderburn-Malsev theorem, and so on, in order to get this proof to work. After the fact, we actually discovered that Grigoriev had used similar algebras, but simpler ones, showing that isomorphism for them was equivalent to graph isomorphism. So it turns out, if you extend them a little bit, you get something that's TI complete. So I just want to end with some open questions. The first is a little bit of a mystery, which is we're used to jumps in complexity from 2 to 3. Like 2-sat to 3-sat. And this happens for tensors also. So 2 tensor isomorphism, a 2 tensor is just a matrix. This is basically just, do 2 matrices have the same rank? So it's in P. 3TI is now universal and TI complete, but not NP complete. So it's in co-AM. So if it were NP complete, the hierarchy would collapse. And so the question is, what's going on here? Is there some more general notion of universality that fits all of these under one umbrella? Some other open questions. Can you get any algorithm better than the q to the n squared? And I just remind you, while poly n would be great, q to the n would solve some of the hardest cases of group isomorphism in polynomial time in the order of the group, which is one of these bottlenecks for graph isomorphism. Are random instances hard for SAT solvers? You know, what can you say using algebraic proof complexity here? What happens over different rings? In fact, even relating tensor isomorphism over, say, F2 or F3 to each other is interesting. All of our results relate problems over one field to problems over the same field. What about other groups? Instead of just saying invertible matrices, you could say I want them to be orthogonal or so on, and you can start to talk about things like lattice isomorphism. So there are lots of interesting problems here. Right, so just to summarize, you know, tensor isomorphism arises in a lot of different places. Many problems turn out to be equivalent to it, and so we sort of gave it this name TI complete. And then one last tiny word, why did we call this part 1? Well, part 2 actually already exists. It's in our archive paper. We just haven't pulled it out into a separate part 2, but if you want a preview of that, you can check it out there. And that's all I wanted to say. So thank you.
Great. Thank you, Josh. And are there any questions? We have time for one quick question. If not, actually, I have a question. So if I understood correctly, a corollary of your result is that checking equivalence between, let's say, degree 4 polynomials, is it the same complexity as degree 3 polynomials? So there is no hierarchy there? Degree 2 would just be matrix thing. So
it's actually a little subtle. I have to think carefully because there's some issues with the fields. And so morally it says that. I don't want to claim without thinking about a little bit more whether it actually says that.
Okay.
Yeah.
Okay. Okay. So let's move on to the next talk then. The next talk is by Ben Volk, who is going to tell us about polynomial degree bound on equations for non-rigid matrices and small circuits. Ben, okay, great.
Yes, all right. Thank you for reading the title instead of me. Yeah, this is what I'm going to talk about. It's a joint work with Mrinal from IIT Bombay. And if you don't know this word, it's fine. I will start from the beginning. Well, first thing is that, you know, we want to prove circuit lower bounds, superlinear circuit lower bounds for strong models, and it's kind of a hard problem, as you probably know. One special case is proving lower bounds from computing linear functions or linear transformation from f to the n to f to the n. F is some field. The good thing about linear functions is that they are computed with a pretty simple model, which is called linear circuits. So a linear circuit is, here we have this definition by a picture. It's a circuit as usual. It's just a graph, but it only uses linear operations. So there are the inputs, and then every inner gate computes, maybe which is there are n inputs and n outputs, and every inner gate computes a linear combination of its children. So the edges are all labeled. So for example, this gate has ingoing edges labeled by alpha and beta. So it just computes alpha times x1 plus beta times x2, and so on. So that's a pretty general and powerful model actually for computing linear functions. If you think of known algorithms for computing, well, what linear functions are there? So one example is discrete Fourier transform or similar things, and FFT, for example, is just a linear circuit, and you can show that any algebraic algorithm for computing linear functions will, in fact, without loss of generality, be of this form. So it's quite a general model, and we want to prove superlinear circuit lower bounds for some explicit linear function. Again, over some field. For this talk, the field will be complex numbers. It's not super important, but let's stick with something. All right, so yes, we don't know how to do it. One way that was suggested for analyzing this model was given by Valiant, and what Valiant proved that if M is a matrix such that the linear transformation represented by M as a linear circuit of logarithmic depth and linear size, then you can decompose M as a sum R plus S, where R is a low rank matrix and S is a sparse matrix. And the precise parameters are rank epsilon n and S sparsity n to the 1 plus epsilon. This is for every constant epsilon. So just as a name, we call a matrix IRS rigid if you cannot write it as such a sum. And we want to find explicit rigid matrices, and it's again an open problem. We still don't know how to do it after many years. We don't know how to do it with parameters that will imply any circuit lower bounds, which these are the parameters, epsilon n to 1 plus epsilon. So we don't do it in this paper. We just, we look at this set of rigid or non-rigid matrices, and we try to say some interesting things about it. And more generally, we look at the set of matrices that, or linear transformation that have small linear circuits, and we say similar thing about it. And I will explain what is the interesting properties mean in this context. For that, I need to give some notation. So let's imagine, we have this set of all complex n by n matrices, and inside it there's this small set of non-rigid matrices. So we know most, there's like those standard counting arguments. Most matrices are rigid. Most matrices require large circuits. So the set of non-rigid matrices is a small set. And it's also, I do it in this weird looking thing because we really don't understand it. We don't know how it looks like. One thing which is very natural to do, I won't have time to explain why it is natural, but take my word that it's very natural, is to move from this is the geometry world, and now you move to the algebra world. And the way you do it is you look at the set of polynomials that are 0 on this set U. This is we denote it I of U. It's the ideal of U. It's actually an ideal. So this is like there's always these two parallel universes. One is the geometry, one is the algebra. And so this is the set of n squared variate polynomials. The polynomial takes some matrix and some polynomial in the input in the entries of the matrix. Now you can also go back from the algebra to the geometry by looking at the set of zeros of the polynomials in I of U. So just to reiterate, you start from U, then you look at all the polynomials that are 0 on U, and then you look at their common zeros. So it's a set that contains U, obviously by definition, but it can also contain more things. So it's called the Zariski closure of the set U. It turns out that in this case, it's actually also the Euclidean closure of the set U. So when you imagine the picture in your head, you can just imagine the regular, usual closure in the complex that you know of. Okay, this set is slightly nicer in several senses. But why am I telling all of this story? The reason is that you can think of a non-zero polynomial in the ideal of U. Well, first we call it an equation of U, and you can think of it as providing a proof that some matrix is not in U. It's rigid, right? P of M is non-zero means that M is rigid just because the way we picked P in I of U, which means it's 0 all non-rigid matrices. So whenever it's non-zero, it means that M is rigid. So P is for polynomial, but also for proof. It actually proves a slightly stronger thing, right? It proves that M is not in the closure of non-rigid matrices, but we'll be happy with even the weaker thing. Okay, but now, so this proof, they exist somewhere in the world, but in order to use it, it's helpful if it's simple, if it's something that we can get our hands on and maybe compute or find or whatever. Well, one theorem that was proved in these two papers by Kumar, Lockham, Patanka, Sarma, and the second is Gesmundo, Harnstein, Eichenmeier, and Landsberg, and they gave some explicit bound on like how large of a degree these equations can have. And they show, well, there's some equation of small degree, and small here means exponential in n squared. And this is a pretty general result. It works for any parameters for which there exist rigid matrices. But one thing that they conjecture is that for the parameters that are interesting for lower bound purposes, so epsilon n and n to the 1 epsilon rigid matrices, you can actually do much better. You can do degree polynomial in n. And in this paper, we proved that this thing is true. So this is the main theorem that there's an equation for matrices which are not, so it's even slightly stronger. It's epsilon n squared rigid. And it has degree at most n cubed. You can even slightly improve this, not super important. Epsilon here is some small constant. It doesn't have to be super small, but it is, I mean, so these parameters are almost optimal. They're like a constant factor away from optimal. And this constant factor is actually what makes us, what helps us get the polynomial bound. We can even prove a stronger thing that you can just look at all matrices that have a small circuit, say size at most epsilon n squared, and you can get a degree, polynomial degree bound for an equation for those matrices. Yeah, so I mean, the proof is not complicated, but I'm running out of time and we didn't plan and I will not say anything. If you watch the full talk, you will get to see basically the entire proof of the first theorem. And we can also prove it for other similar models like 3-dimensional tensors of low rank. The main downside, the open problem that I will finish with, is that the proof it's non-explicit. It doesn't give an explicit equation P. Explicit here could mean an equation with a polynomial size arithmetic circuit, for example. There is a win-win phenomenon in the sense that if there are explicit equations, of course, it's great because now maybe we can prove these lower bounds. If there aren't, it's also great because we are sort of pinpointed a family of hard polynomials. So you can sort of make it into a formal theorem. But the main open problem is really deciding on whether explicit equation exists or even coming up with explicit equations. Okay, I think, sorry for running a little bit out of time. Like, that's the end.
Okay. Thank you. And the last talk of this session and the conference is by Thomas Taylor, who is going to tell us about sum of squares bounds, how they imply circuit hardness and de-randomization.
Okay, do you see my slides?
Yes, yes.
Okay. Yes, this is about sum of square representation, and lower bounds rate implies circuit lower bounds. So let's start with sum of square representation. This refers to polynomials. There are various settings where sum of square representation is considered. So we have here a weighted sum of square representation because we allow these coefficients from the field.
Thomas, sorry, can you speak a little louder because I think, yeah, or raise the volume, increase the volume a little bit.
Is it better now?
I think so, yeah, yeah.
Okay, okay. So in mathematics, this would be called a weighted sum of square representation because we allow these coefficients. There is a famous Lagrange, the Hilbert 17th problem about sum of square representation, where this coefficient is not allowed. So Ci is 1 here, and then it's only for positive. And Hilbert asked which polynomials can be represented that way. Also, there it was multivariate. So here we consider univariate polynomials. As the complexity measure, we use the sparsity of the FIs in the representation. So sparsity is simply the number of non-zero monomials, the number of non-zero coefficients. And this we sum up, and this defines the size of F with respect to one such representation. And then the support sum is the minimal way you can represent F that way. So in our case, any polynomial can be written in such a way. Simply by this formula, you can easily check that when you multiply out, you get back f. And for this complexity measure, so consider the case that f has full sparsity, which means there are no non-zero coefficients. That means the sparsity is degree +1, d +1, d is a degree. And then the support sum is between these two bounds. The upper bound you can see from this equation here, because we have two expressions and each of them has sparsity d +1. The lower bound you get by a counting argument. When you take squares, you have to have at least square root d many monomials to end up with d monomials. So the bound is between square root d and linear in d. I have two examples, so that's easy to check here. So look at this polynomial, and then you can verify that you can write it as a product in this way here. So let's call these two brackets u and v, and observe that sparsity of each bracket is square root d. And when you have such a product, you can write it as a sum of squares by this formula here. So when we now look at the support sum size we get, then observe that u and v both have square root d sparsity. So when you take u plus v or u minus v, you get 2 square root d. And so the support sum is bounded by 4 square root d in this case. So this is essentially at the lower bound, except for the factor 4. If you look at this polynomial, suppose for simplicity that d is even, then you can write it that way. And that means that the support sum is bounded by d by 2, because you have the sum is just one term here. So that's a trivial example. But this bound is more at the upper bound. And actually, we think that the value is indeed around d. And similarly, for other polynomials, we have several candidates like this here, or this polynomial, where we also think that the support sum should be around d. So why is this interesting to consider? There's a connection to circuits, and we have just seen a arithmetic circuit in Bentley's talk. So VP is the class of all polynomials that can be computed by poly-size circuits, and VNP is the class of polynomials that can be written as exponential sums of BP polynomials. So these are the arithmetic analogs of P and NP, and goes back to Valiant that the permanent function can be seen to be complete for VNP, and the conjecture is that it has super polynomial size circuits, which is equivalent to say that VP is different from VNP. So this is the ultimate goal here to show. So coming back to sum of square representation, we call a family hard if the support sum size is a little bit bounded away from the lower bound. So d to the half plus epsilon. And actually for our purpose, epsilon must not even be a constant. It can be a function depending on d. It just has to be larger than this decreasing function. And the purpose is this theorem here, what we show. This is one of our main theorems. We show that when one can show existence of a hard polynomial, which means the support sum is as of this size, this already implies VP different from VNP. So observe that this is somehow surprising, because here we have a univariate polynomial, whereas this considers multivariate polynomials, and sum of square representation is really a simple way to express polynomials, and we just require to be a little bit away from the lower bound. And anyway, this implies VP different from VNP. I will not go into the proof here. You get an overview on the proof in the extended talk, and for the full proof, you have to look in the paper. In the stronger formulation with constant epsilon, we actually get a exponential separation between VP and VNP. That's a little bit different proof. Some results that are somehow related is also sum of square representation for low bound implies exponential low bound for the permanent. However, this is in the non-commutative setting here. And also the lower bound here uses a little bit a different complexity measure. So this result you cannot really compare with ours. And there is Korea, who also has a similar looking theorem that is that when you have a representation like this and S is large, that also implies VP different from VNP. This is also univariate. However, the exponent here can be larger. So we have exponent 2. That is quite essential. Yeah, what open questions are, can we decrease the hardness bound and still get VP different from VNP? In the title, there was also hardness to randomness mentioned. So we know that VP different from VNP implies that polynomial identity testing can be done in sub-exponential time. We also consider sum of cubes representation in the paper. And there we show that a hard polynomial would actually imply that polynomial identity testing is in polynomial time. It also implies VP different from VNP, but gives a stronger derandomization result. However, I cheat here a little because what I hide in the hardness here is a bit stronger than the one we used for sum of square representation. And the main challenge is now to really prove a lower bound for sum of square representation. That looks like is doable, hopefully. Thank you.
Thank you, Thomas. Well, that was the session. So let's now move on to the panel discussion. And I have a few questions, but we can start with questions from the audience if any of the speakers wants to raise any questions. Okay, I have a question from the audience for Ben Lee. I'll just read out the question. Could you clarify p-space in case of circuit transformations?
I'm not sure I can understand the question, so I don't know if if the person who asked it wants to ask it.
I think they're asking about like where does the p space come from?
Okay, I don't think I mentioned p space in my talk. In the paper, there is I mean, I mentioned this sort of there's like a win-win result. Or I mean, maybe I should say the point is that the equations we find are, as I said, they're not explicit, but there's, I mean, it's just solving some system of linear equation, and there is a system. There's a p-space algorithm that just outputs the equations like as a list of coefficients, the solution to this linear system. And now the point is that you know, either this is a family of hard polynomials, and then it's great because we don't know how to find in p-space a family of polynomials with super polynomial circuit complexity. But if it isn't, then you can do some other thing and get some other lower bound.
So I actually have a question for Nathan. I'll start a bunch of questions, unless somebody else wants to go first. Well, if not, let me actually ask Nathan a question. So you gave a bunch of examples of different kind of domains, combinatorial domains, and how different measures of complexity generalize, or like polynomial equivalences hold. Is there an example of like a theorem but relating measures of complexity in the Boolean domain, which does not seem generalizable?
Let's see. So I think, let's see.
I mean, maybe more generally.
I'm sure there is, but at least.
Well, maybe. Yeah, sorry. In the spirit of the conference, let me make the question very general. There's a lot of this work. Okay. There's a lot of work which is like, you know, this domain, like whatever we know about Boolean function analysis, that carries over to bigger domain. That carries over to more complicated domains. What seems like a feature of the Boolean domain, which is of the hypercube, which is very specific to the hypercube? Maybe complexity measure, maybe some KKL theorem. I don't know. Like I'm just throwing it, like something which just seems like, you know, this is never going to work out in something else.
Yeah, that's a good question. So basically, anywhere where you're using like where you're using nice things about the characters of the hypercube, that does not translate to these non-abelian settings. So there's plenty of results in the analysis of Boolean functions that use the fact that the characters of the hypercube form an orthonormal basis, and then you can do, you know, you can throw a lot of probability theory to solve some of these questions. That just doesn't work in these more abstract domains. And then in one really, I mean, there's, I think that's like the fundamental difference I would keep in mind between these things. But there are things like hypercontractivity and things like that that have been studied on the hypercube that also carry over to the symmetric group. So there is some recent result by Filmus, Menzer, Kindler, and I want to say maybe Noam Lifshitz as well. So you can, there are things that carry over, but I'd say it's the characters that's the fundamental difference between these different domains.
I can see Adrian, why don't you go ahead? Okay.
Yeah, sorry. Yeah, I had a question for Josh. On your last slide, you have an open problem related to algebraic proof complexity. And I was just wondering if you can make that a bit more specific, and is there any relationship to what you previously said about the ideal proof system?
Yeah, so I guess it's not specific to the ideal proof system. It's really like if I give you two tensors and I want to prove to you that they're not isomorphic, you can write down a system of polynomial equations which is unsatisfiable if and only if the tensors are not isomorphic. So like solutions to the polynomial equations are change of basis that give you the isomorphism. And so then you can use whatever algebraic proof system you want to try and prove that this system of equations is unsatisfiable. So you could use Stahlensatz or PC or IPS or restricted versions of IPS, whatever you want. And actually, in the context of graph isomorphism, there's a very nice paper by Harm Dirksen where he essentially does that for graph isomorphism with polynomial calculus. Yeah, so there's also a question of like, can you extend that work from graph iso to tensor iso?
Right. Yeah, that sounds like a very, very natural thing to consider. Yeah, thank you.
Are there other questions? Anyone else? Okay. Actually, maybe I have a question in the context of the last talk, Thomas. So, so you were considering sum of squares lower bounds for univariate polynomials. Are there like similar natural easy upper and lower bounds for? Okay, maybe for multivariate polynomials, is it true that every multivariate polynomial can be written as a sum of squares? And are there like natural upper and lower bounds for complexity measures? And if so, what would it imply for separation of VP and VNP? Actually, I don't see Thomas here. So no, I don't see Thomas here. So okay. Okay. Thomas. Okay, Thomas says okay. Okay, Thomas. Okay, it's actually midnight. It's actually past midnight in Germany. Okay, okay, okay. So let me. Okay, so are there other questions, or we can maybe like start discuss another paper?
Hi, sorry, Josh mentioned this thing about the difference between 2 and 3, and somehow, is there anything we know about that, or anything more you can say about it?
Yeah, so it's not specific to 2 and 3. Really, like if you look at tensor isomorphism over any two different fields, even in the same characteristic, like F3 versus F9, we don't know what the situation is. And so it's like those, if you talk about tensor isomorphism, even over different FPs for different primes P, it's like, we kind of know what I said. You have the brute force algorithm, they're all in NP intersect coam, but we don't know reductions between them. And they would really have to look different than the things in our paper. I mean, the things in our paper are really very algebraic. They work over whatever field you're working over. Yeah.
Thanks.
Josh, you require the field, sorry, for your isomorphism results, you require the field to be of a sufficiently large size or something, or any field is fine?
Nope, any field is fine, except for the things about polynomials where like sometimes you need to be able to divide. Like for degree 3 polynomials, you need to be able to divide by 6, for example, to get some of the equivalences. Okay. Yeah. And actually, Ninja, about your previous question about degree 4 versus degree 3, I forgot before, that actually already follows from previous work of Agrawal and Saxena, with one little thing, that the reduction from degree 3 to degree 4, there was a little complication, but the rest of it is all in Agrawal Saxena from 15 years ago. Yeah.
Are there other questions? Okay, I still have my list of questions actually. So one question for Ben Lee was, so regarding your thing about getting explicit equations. So what does explicit exactly mean here? Like you want to, I'm actually not entirely sure, like some, is a polynomial time? Like what's the, what
yeah, I guess, I mean, it could mean what you want, basically. Okay. I mean, one formal notion you can think of is, well, it's a polynomial, so explicit means having a polynomial size arithmetic circuit. Of course, it's arithmetic circuits are a non-uniform model, so it's kind of a weird thing where it can have a circuit which you have no idea how to find. So of course, like the best thing would have to be, explicit in the sense that you can write it in a one line in LaTeX and compute it. That would be the best thing. I don't know how much you should expect at this point, but yeah, you can make it. I guess the bottom line, you can make it. You can use any definition you want, and anything would be interesting.
Actually, in the spirit of the conference, let me again ask a super open-ended question. So we saw a lot of measures of complexity being discussed. There was a measure of like the Boolean function analysis kind of measures of complexity. There were, or like, things appearing in algebraic complexity or widgets. Could there be potentially some relation between these? That was really open-ended. So I don't have an answer, but I just thought like, in the spirit of the conference, let me throw it out there.
I don't know. I know Eric Allender, who I see is in the audience, has some results about this.
Let me. Okay, maybe I can just. I can. Okay, Eric, if you want to add something.
I don't have anything very profound to say. Certainly, there was a paper I did with Anna Gall and Ian Mertz, where we were looking at various classes of algebraic circuits and relating them very directly to certain classes of Boolean circuits. Peter Bürgesser had some results quite a while ago relating non-uniform complexity in the Boolean model to algebraic complexity, just relating various open questions. And there's quite a few results of that form. But I'm not sure if that was really what you were getting at, or if Josh was thinking of something different.
No, I think that's what I was thinking of. I don't know if it's what Anindya was getting at. But
I was not really getting at anything in particular. I was just thinking of just like throwing something out there. But yeah, no, this is a good answer to my vague question, though.
Kind of interesting. I mean, I don't know that I've seen anything about, for example, like sensitivity and that kind of thing in the algebraic setting.
Yeah, I mean, maybe like, I guess related to something I asked earlier, then in the Boolean function world, I guess a lot of not complexity measures per se, but things which are like, actually, yeah, sensitivity is a complexity measure where you're really thinking about like isoperimetry, right? Like, how much surface area is there. And it's not clear, like, if those kind of notions necessarily always generalize to other domains. And maybe those kind of things can also be hard to talk. I guess, yeah, like, I without an underlying metric, I find it very hard to think about things like surface area. What would it mean if you perturb the function a little bit? And now if you think about finite fields or where most of algebraic complexity is done, is there a notion of metric? Is there some metric you can endow the domain with?
Sure. So there are natural notions of a metric space for permutations, perfect matchings, subsets, and things like that. And in our I didn't have time to discuss it, but I think we give a satisfactory definition of sensitivity in the domains of the symmetric group and perfect matchings. But as one of my open questions states, we weren't able to extend this to, like, say, hypergraphing or hypergraph matchings or things like that. So yeah, I think they're well defined. And in fact, like, noise sensitivity was even studied before our work, which is slightly different than the definition that we give in our paper. So check out works by Carl Wimmer and O'Donnell from like 10 years ago. Yeah, you might find that interesting.
Yeah, I mean, somehow, like, I guess, like, those works are like, there was a graph, and so there was naturally some sort of a metric defined because there's an edge, so you know what this moving by one means. Just wondering, like, I guess in the finite field or something, it's not like 3 comes after 2 and before 4, like that notion might not be there. So finite fields, it might be a little harder to define metric. But again, like, I didn't have anything particular when I asked.
I think you're touching upon some of the difficulties that even we encountered when trying to wrestle with some of these Q analogs. So like like Grassmann graphs and things like that. I mean, it's difficult to capture them in our framework. So that's one of our open questions. So yeah.
Are there any other questions? We can keep the discussion going. This is the last session of the conference. Okay, Ovi has a question, but he's typing the question, so we'll wait. In the meantime, if somebody else has another question. Okay, there is a connection between okay, if Uvi is sorry, Uvi, you can also unmute and ask, like you don't have to type the question. Okay, I'm reading out Uvi's question. Sorry, Uvi. Okay, I'm reading out Uvi's question. Oh, his mic is jammed. He says, there's a connection between influence and the probability of probing in a decision tree algorithm. Might that extend to more than just a Boolean setting? I guess there are decision tree construction algorithms where you look at the influence of the variables. I think the result is BKKKL. Okay, yeah, the BKKL. So might that extend to more than just a Boolean setting?
It's yeah, I'd have to take a look at that result to say one way or the other. I'm not familiar with it, but let's see. So yeah, I mean, I guess this is another open question that I didn't state. I mean, we only had, I mean, our paper was already 60 pages with just the complexity measures that we mentioned in that paper. So you have to draw the line somewhere. And so I would be interested in seeing if other nice results in the analysis of Boolean functions, if you can find analogs for these other more complicated domains. And if the ingredients are just decision trees and a notion of influence, which you get from definitions of sensitivity, then it seems quite possible, but I don't want to say for sure one way or the other.
Josh actually had a question for you. It was a clarifying question, really. So you said something concerning that, something about tensors, the notion of tensors in machine learning, and how, like, something is a genuine tensor. I do not know how tensors differ from an array of numbers. So, yeah. So what's the notion of a tensor?
Tensors, like for an array of number to be tensors, it should really be like you should have a notion either of like a way of contracting it with another tensor, like multiplying a matrix by a vector,
okay.
or like change of basis, where there's some vector space floating around, and if you change basis in the vector space, it changes basis linearly or multilinearly in the tensor. And so there are lots of like TensorFlow is mostly not actually about tensors; it's just about high dimensional arrays. But my point was there are actually some sort of genuine tensors that are like multilinear algebra that show up in machine learning. Yeah.
Okay, so you're saying like it's not like sorry, go on. Sorry.
No, yeah.
I was just going to say like so you do not. You're saying an array of numbers can be a tensor, but you have to endow it with some other operations, like you have to define a notion of contraction and transformation, something else. Like it cannot just be an array of numbers in itself makes any.
Right.
Really.
Same way for a vector or a matrix. Like, yeah, I could call any array of numbers a vector, but I only do that if I'm going to treat it as a vector in a vector space, right? Like, yeah.
Fair enough. Are there any other questions? Anybody else wants to pose a question or have?
Well, I had a question for Nathan, actually. So you mentioned in this like abstract simplicial complex framework, you sort of always have some action of Sn floating around, and like it's the representation theory of that somehow gets things started. Do you have things for if you have an action of some other group on your universe?
Yeah, so this gets back to the question of Q analogs. So we tried doing something with like say GL and Q acting, and it just I mean, we just couldn't like, I guess the best way of saying this is that like there is no like natural way of talking about say like k element subspaces in like some or sorry, k dimensional subspaces as being like some sort of simplicial complex, and it's or at least I'm not aware of it, and that's sort of I think at the heart of like why other actions like say like GL and Q they don't like fit into our framework. Yeah, that's a good question though. I mean, it's like for combinatorics, we chose SN because that's, there's even that quote, right? Like, yeah, maybe it's, yeah, I forget who said it, but like all of combinatorics can be encoded as like representation theory of the symmetric group. It seems a bit bold, but I think somebody said it before. So, so yeah, that's why we chose SN. So, but yeah, are there other groups? I don't know. That's a good question.
Are there any other questions? Anybody else has any remark? Well, if not, then actually let's thank all the speakers in this session, and we can then end the panel now. Thank you.